Justin Miller, Acton College Physics here. We are going to start looking at some magnetic field interactions. Ooh, we looked at electric fields, due to charges, charge configurations. Now we're going to throw in some magnetic fields too and see what pops out of here. So, what do we got right here? I got a battery, a nice battery there. Great. I've got an alligator clip. I've got a black wire and a red wire connected. Red wire's connected here. Black wire's not. Black wire's not. So, what I want to do first is just take a magnet. I've got a nice horseshoe magnet, like Wile E. Coyote. Show that it's a magnet, right? Okay, it picks up something that's magnetizable, like steel. Whoa, look at that. Don't get your fingers pinched in that. And then what I want to do with this is just kind of put it around these wires, see that nothing happens, even though inside these wires there's copper wire. Copper's not magnetizable under normal circumstances, so it doesn't interact with the magnetic field. You can't pick up copper with a magnet, basically. The ends, however, have some steel on them, and well, actually these ones don't, so never mind that. The battery does. I don't want to track the battery though. So actually there's a little tiny bit. That's okay. I'm going to stay away from the ends. The main thing is that the copper portion here that's underneath this insulative coating doesn't interact with the magnetic field because, well, again, it's not magnetizable. So what I'm going to do is I'm going to plug the red wire in to the battery, and that's going to establish a current, right? There's some amount of resistance, there's the source potential, and then we got a completed circuit here. So even though we don't see it, right now there are electrons flowing around in this red wire. Well, that's great. What I want to do now is see if anything happens. So I'm going to take this same magnet here, didn't trick anything, and I'm going to take it around these wires, say, well, the black one doesn't seem to do anything. Ooh, you may see the red one moving a little bit. Black one doesn't do anything. Black one's not plugged in. The red one is. And what do we get here? Whoa, do you see that? We get a sort of attractive force between the magnet and this wire. Ooh, now it's repulsive. Repulsive, let me turn this magnet around like this. Oh, now it's attractive. So I can get repulsion or I can get attraction depending on the orientation of the magnet. So really what we have here is some sort of discernible interaction between the magnetic field due to the magnet and something about what's going on in here. What's going on in here? We got moving charges. The red wire has moving electrons, the black wire does not. We don't get any interaction with the black wire. Nothing happens, but the red wire, we do. Why? Well, you can kind of make a judgment call there and say it must have to do something with the electrons moving in this. So I'm going to go ahead and take this out, disconnecting the circuit effectively, and see if we still get anything. And the answer is nothing. No repulsion, no deflection, no attraction. It's only when it's actually plugged in do we get anything. So you can pretty much go figure then that there's something about moving charges. What it turns out is that moving charges within a magnetic field may be or may have a magnetic field force exerted on them. Some of it depends on the orientation of the magnetic field with respect to the direction that the charges are moving. This is what we want to get. We want to be able to first establish that, hey, there's a magnetic field force that's possible on moving charges, and then kind of go from there. So, let's just kind of roll this on out here and spell some stuff up. We'll say the magnetic force on a moving charge is given by F sub b hat, that's going to be the magnetic field force, is equal to the cross product between the velocity vector of the charge and the magnetic field vector. And it goes like this. It is Q times V hat cross B hat. That's the formal expression for the magnetic field force on a moving charge Q. F sub b hat is the magnetic field force. Q is the charge on which the force is exerted. V hat is the velocity vector of the charge. And B hat is the magnetic field vector at the location of the charge Q. Vector, vector. This, of course, we've seen before. Cross product. Where have we seen that before? Torque, right? We had the torque was a cross product between a radial vector and the force vector. Well, this is another cross product relationship, but there's some things that we need to be able to sort of extract from this. But the premise with all this is, hey, moving charges may be subject to a magnetic field force if they're indeed immersed within a magnetic field, and there's a non-zero cross product between the velocity vector of the charge and the magnetic field vector. So let us resolve this out. We can always take this and just talk about it in terms of what's the magnitude of the magnetic field force? Well, the magnitude of the magnetic field force, little sub B there for magnetic field, that's what we're going to use for magnetic fields, B. Well, that is going to be Q VB times the sine of theta. I'm going to put absolute value of Q times V times B times the sine of theta. We've seen this before. This is how we resolve cross products and extract out a magnitude. This is just how much charge, absolute value, because we don't want to have a minus sign in magnitudes if the charge happens to have a negative amount of charge. V is the speed, B is the magnetic field strength, and theta is the angle between V hat and B hat. Theta is the angle between V hat and B hat. So what can we see with this? Well, we'll have that the magnitude of the magnetic field force will be equal to 0 if what? Well, basically, if this is equal to 0, when's the sine of theta equal to 0? Well, if theta is either 0 degrees or 180 degrees. That is to say that if the direction that the charge is moving is in line with the direction of the magnetic field vector, at that point, there's no magnetic field force exerted on it. Cross product requires that there be mutually perpendicular components between the two vectors in question here. So that's one thing that could happen. That's why we say there may be a force exerted on a moving charge within a magnetic field. It depends on the direction that it's moving with respect to the direction of the magnetic field. And we would have this as well. F hat sub B is equal to a max value of QVB if theta is equal to 90 degrees. And why don't we say, well, can theta be 270 degrees? And they say no, because it's the small angle between two vectors. So this is something we say theta for our purposes here. Theta is some angle that's less than or equal to 0 degrees, less than or equal to 180 degrees. So you may have something, say, where magnetic field vectors like this, say, and we could take our charge, say, well, we've got some charge Q, and it's moving, say, in that direction at some point in time. Well, there's this angle here, that is the angle between those two vectors. One could also say that, well, what about this angle here? Well, that one isn't the angle that we're talking about. Doesn't end up really mattering, but we want to use the short angle between the two vectors in question here. So that's how we discern this. Now, if again, V is in the same direction as B, we have theta is equal to 0 degrees, thus there is no magnetic field force, or if it's traveling in the opposite direction of the magnetic field, there is no magnetic field force. It's only the perpendicular component of the velocity vector that gives us a non-zero magnetic field force. All right, so that's all pretty cool. Some things to note here. SI units of B hat. We've got, it's a vector quantity, the magnetic field force. It has units of, well, we could kind of rearrange things if we wanted to. Rearranging, say that, and say, well, it has to have units of force divided by charge divided by velocity. So I'll just kind of look at this. We could say it has to have units, force divided by charge divided by velocity. We're just looking at magnitude. Right, so what would we get out of this? Well, force, doesn't matter what type of force, we're using SI units. We've got newtons. We've got coulombs for the charge. And then we've got meters per second for the speed. Well, we've got a Newton second per coulomb meter. You say, well, those are kind of funky units. We could also break up N into what it's built of, right? Mass times acceleration, kilogram meters per second squared. We could reduce this down, but in the end, we're going to call the magnetic field units one particular thing, and that is Tesla. Capital T4. That is the SI unit of magnetic field strength, the Tesla. That's great. There's some other unitizations, CGS units and some other ones. You can use Gauss. We're going to use Tesla because, well, again, we want to stick with SI units. So as long as we're measuring the magnetic field strength in Tesla, the speed in meters per second, and the charge in coulombs, we'll get that the force is in newtons. That's what we're going to stick with. So there we go. We're going to measure it in Tesla. I just like saying Tesla. Anyways, that's what we've got going on. So finding the magnitude, pretty easy. If you know the orientation of the direction of the charge with respect to the direction of the magnetic field, you know how fast it's moving, you know how much charge it is, and you know the magnitude of the magnetic field, boom. You just plug everything in and get yourself the magnitude of the force. But there's always just more than magnitude when we're talking about vectors, right? What about the direction? So we've got F sub B hat. What about the direction of the force? Well, that's a little bit more involved, because the cross product takes two vectors and forms another vector that is perpendicular to both of the two original vectors of which it is composed. So F hat has to be perpendicular to both V hat and B hat. By the cross product, F hat sub B is perpendicular to both B hat and V hat. So if we have something sort of in this orientation, that leaves us with know two possibilities just based upon that statement here. So if it has to be perpendicular to both that direction and that direction, it basically has to be perpendicular to the plane of this board. Again, for these two vectors, how they're drawing out, which would leave us with that force either being out of the board or into the board. And that is something that we need to be considerate of. When we're dealing with torque, we didn't really need to understand completely the directionality, because we just said, oh yeah, it's going to rotate this way or it's going to rotate that way. We could say clockwise versus counterclockwise. We're only doing things kind of one-dimensionalizing something that was three-dimensional. That was easy to get away with. Here you can't really do that. You've got to be a little bit more definitive because, well, you could have multiple forces acting and we want to know what's the net force. You've got to be able to determine what direction things are. So that brings us to kind of the next portion of this and figuring out what is the direction. So there's a couple different ways of doing this. There is I want to say an easy way, but what's known as the right-hand rule. Maybe you've run across the right-hand rule before, maybe not, that's okay. And then there is using determinants and matrices and actually mathematically utilizing the cross product, what it really comes from. So we'll take a look at both here. Let me erase this stuff. I'll come back and get this going. Be right back. All right, so we want to look over at the cross product. So we're going to do it the nice mathematical way first, and then we'll utilize the right-hand rule, which is what we'll mostly do in this class. But cross product comes from, well, taking cross products of two vectors. So what we're going to do here is sort of like map out how this occurs. So if we say what is A hat cross B hat, well, the way that it's done mathematically is with Cartesian coordinates. We have these vectors could have an I hat, a J hat, and a K hat component. So do it with 3 dimensions. And what can we say? Well, we can say that A hat is like some A sub x I hat plus A sub y j hat plus A sub z k hat. And likewise, we can say that B hat has some B sub x I hat plus B sub y j hat plus B sub z k hat. So we break them all down into x, y, and z components. And then in terms of doing the cross product, this is how it's approached. We take ourselves the x, the y, and the z components of each of these vectors and go ahead and throw them here. I have some a sub x, I have some a sub y, and I have some a sub z. And I have also got a's being crossed into b, so a goes first. And then we've got b sub x, b sub y, and b sub z. You say, okay, you just make a nice little box with them. That's exactly what we've done here. And now what we want to do is actually use a cross product. So a lot of times you'll see that this is kind of taken out like this. Put these here. So if we want to get the mutually perpendicular components of each of these vectors and multiply them together, we have to do it component by component. So we've got that j hat's perpendicular to k hat, I hat's perpendicular to j hat, and k hat's perpendicular to I hat. They're all mutually perpendicular with respect to one another, right? So we just have to multiply out the mutually perpendicular components and form another vector or another component that's perpendicular to both of those. Yeah, that's right. All right, so how does this play out then? So what we do first is say, well, let's figure out what the I hat component of the cross product is. So ultimately, this is what we do. We say we're going to look at the I hat component. Well, the I hat component is going to be the cross product of the j hat and the k hat components of the two vectors here. So how is that? Well, we go that and that. The cross product. So AY times BZ, and then we got BY and AZ. How this plays out is this. We've got this vector here, let's just call this, is equal to some new vector C hat. We have that C hat is going to be equal to, you have AY minus BZ, oops, sorry, minus AY times BZ minus BY times AZ I hat. There is the I hat component of the cross product of A crossed into B, but that's just the I hat component. There could be a J hat and a K hat component too. So what do we do now? Well, we say, okay, let's check out J hat component. The J hat component is looking at the mutually perpendicular components of A hat and B hat, which are the I hat and J hat components, and doing the same sort of cross product thing. So we've got this. We've got an AX and a BZ, and a BX and an AZ. Got to be careful with the J hat component because there has to be a certain configuration of cross products sign-wise. So it's got to be a little bit careful with this. So you'll find it kind of written out differently in different books. I like to generally say that I'm going to go the same way, A, B, A, what we just did there. But in the case of the J hat component, it ends up being negative. So we write this out. Negative, then I got AX times BZ minus BX times AZ. Which we could just distribute the negative sign through and flip that around. That would be fine too, but that is the J hat component. And you may say, well, why is it negative? I'll get to that. There's a good reason for that. Well, we've got one last thing to look at, and that would be the K hat component. So we look at the mutually perpendicular components of A hat, B hat with respect to K, and we've got this. We've got the X and Y components of the two vectors. So we've got AX, BY, BX, AY, and we've got plus AX, BY minus BX, AY, K hat. And there we go. That's how we form the three-dimensional cross product from two vectors. So this vector C hat is now a vector that is perpendicular to both A hat and B hat, and has a magnitude of AB times the sine of beta. You've got to be a little bit careful of that because we could have some other angles going on. But not going to get into that. We're keeping things like this. Anyways, that's what we have here. So that's kind of the formal mathematical way. And now for that negative sign. Well, Cartesian coordinate systems must be arranged in a certain way. That is the x-axis, y-axis, and z-axis to satisfy cross-product relationships. I don't know if you remember going through three-dimensional coordinate systems the first time, and they said, well, change it to 3 dimensions. Now we're going to say that x is coming out of the board, y is going that way, and z is up. And I remember going, well, why do you want to say x coming out of the board? Why can't we just say x, y, and then z is coming out? Or z is going in? Why do you want to reconfigure it all and make it not so directly associable to just a 2D system? And I never really understood that until it was explained to me utilizing cross products. So the Cartesian coordinate systems must preserve cross products relationships. We must always have that I hat cross J hat is equal to K hat. So I crossed into J gives us K. J hat crossed into K hat gives us I hat. And the K hat crossed into I hat gives us J hat. if you flip the order of these, you get a negative sign. So if we go ahead and say, well, what about j hat? J hat. So your unit vectors here. A j hat component crossed into an I hat component. Well, that's negative k hat. If we switch this around and say k hat crossed into j hat, what's that? That has to be equal to negative I hat. And then you got yourselves that you take I hat and cross it into k hat, you get negative j hat. Let's go back to this red one here. That's where we had, looking at the j hat component, right? And see what we had. Well, doing it from this side to this side, we went ax times bz minus bx times az. That was looking at the I hat crossed into the k hat. Well, I hat crossed into k hat gives us a negative j hat component. So that's where this negative comes in, is because of the way that we've done this. Now I've seen some other ways of looking at the determinants and adding on another I hat over here, and then it's a little bit easier sometimes, but ultimately that's what we've got. So that is formally what we have to have. So if you ever have a coordinate system, three-dimensional, and you know what's the x-axis and what's the y-axis, there can only be one direction for the z-axis. It can't just be, oh, I'm just going to make the z-axis up or down. It depends. It depends. So let's say this. Let's say that that's our x-axis, and that's our y-axis. What direction is the z-axis then? How would we figure that out? You may just want to say, oh, it's out, or you may want to say it's in. There's only one that it could be. Well, x is I hat, y is j hat. We have to have that I hat crossed into j hat gives us k hat. That's how we ultimately compose the directionalities. Now you may say that, well, that doesn't really answer the question, which is it, in or out? And that's where right-hand rules come in to be really handy in terms of giving you the orientation of things. So you can take your fingers, your thumb, and really your palm like this, but a lot of times you just see this, middle finger, index finger, thumb, and form a three-dimensional orthogonal basis here. That is, this finger, and this thumb are all perpendicular to one another. And the cross product ultimately can be composed in terms of a right-hand rule, directionally. So that's what we also want to be able to do. Right-hand rule. Cross products. Cross product directions. So there's variations of this. As long as you use one that's correct, you always get the right correlation with directionalities. So if we say we've got some A hat crossed into B hat, which gives us some new vector C hat, and we want to know what is the direction of C hat without having to go through all of this stuff, well, you can do fingers on right hand, fingers point in the direction of A hat, orient your palm into the direction of the component of B that is perpendicular to A hat. And then your thumb then extends into the direction of c hat. So, fingers, palm, thumb. If you can write out vectors or draw them out, you can figure out what direction the resultant vector is in terms of the cross product. So let us come up to this right here. We have that, if we say x positive that way, hey, that's the positive I hat. What is that? That's the positive j hat. And we must have that I hat crossed into j hat gives us positive k hat. So if I go ahead and look at this, I have an I hat crossed into j hat. Fingers, palm, then thumb. Fingers in the direction of I hat. Palm oriented in the direction of j hat. My thumb then extends into the direction of k hat, which means that k hat then is out of the board. Out that way. It cannot be in because the cross product wouldn't be correct then. So that's how we have to compose three-dimensional Cartesian coordinate systems such that these cross product relationships are preserved. So if we went j hat crossed into k hat, that would give us I hat. Well, j hat's up, k hat is out. Hey, I hat, that's right, that's right. We also have to have the k hat crossed into I hat gives us j hat. Well, we said the k hat's out, so if I point my fingers out and cross it into I hat, which is, oops, k hat is out, I hat is that way, palm faces in that direction, and my thumb's up in the direction of j hat. Perfect. If that wasn't the case, that wouldn't be a proper Cartesian coordinate system. All right, so that's how all this cross product stuff plays out. What we want to do is associate it back to magnetic field force. You may say, whoa, what were we doing all this for? And the magnetic field force vector, which was the cross product between the velocity vector and the magnetic field vector acting on a charge. So, yeah, let's take a look at that. All right, so let's just keep on looking at this stuff and utilize this right-hand rule a little bit. So for our consideration here, this is what we've got. We've got the magnetic field force vector on a charge q moving with the velocity v in a magnetic field b is given by this expression. This is what we really want to be looking at in terms of the direction, right? So we've got, yeah, the magnitude of that force is just absolute value of q times v times b times the sine of theta. And then, well, what else do we have? We've got the direction. And we're going to generally stick with vectors that are either in the plane of the board or perpendicular to the plane of the board, which gives us the ability to sort of, well, just have this one angle that we're dealing with and talk about in, out, up, down, left, right. Anyways, for the directions, we want to look at v hat cross b hat. So as long as q is positive, this will give us the right correlation here. So this is what we got to do, what we'll look at here. Let's say that we have some charge. Consider positive charges. We could have, say, well, the charge is moving this way. There's its velocity vector. And let's just go ahead and say, well, let's say that the magnetic field vector is downward like that. And what do we want to know? We want to know then, what is the direction of F sub B? What's the direction of the force of this charge? So this charge is moving at this instant that way. The magnetic field at that instant, at the location of the charge, is that way. What direction is this magnetic field force at that instant? So it's V hat crossed into B hat, right? So fingers crossed into palm gives you the thumb. That's it. So fingers, palm. Fingers, palm, thumb. So first one, fingers, hey, that's the direction of the charge that it's moving. Palm goes into the direction of the magnetic field, which is down, so my palm faces down. And my thumb extends into the direction of the magnetic field force, which is then into the board in this particular case. So we can write that, oops, it's X, F sub B. So let me say, well, what do you mean X? So if you haven't seen this before, into the board, we use an X, out of the board, we use a dot. Why an X and a dot? Well, it's supposed to be kind of representing an arrow, right? That's how we represent vectors. And well, the X is supposed to be like, you see the tail feathers of an arrow going away from you. And the dot's like, you see the point of the arrow coming towards you. That's the correlation that it's trying to make here pictorially for the drawing into the board versus out of the board. X is in, dot's out. All right, so we've got that must be the direction of the magnetic field force based upon cross product. Again, assuming it's a positive charge, you may say, well, what if it's a negative charge? It's just in the opposite direction, 180-degree rotation. The opposite would be out of the board. So if this happens to be a negative charge, the magnetic field force on it would be this way. That's something you've got to be careful of, but usually we just use the right-hand rule. If it is a negative charge, then you just rotate it by 180 degrees, opposite direction. Let's do some more of these, right? What if we've got ourselves something like a V hat and B hat like that? What about that? Well, fingers go into the direction of V hat, whoosh, palm faces into the direction of B hat. So you may say, well, I can't go like this and have my palm like that at the same time. But we have to remember this is really the perpendicular component of B with respect to V. So we could kind of say, well, the perpendicular component of B would be more like this, be perpendicular to V. Yep, that way. That's what we really want to look at. So V's that way, crossed into B's that way, thumbs out of the board. We've got ourselves then, for this particular case, F sub B hat would be out. Just in there. Well, we could look at some more of these. What happens if we had something like this? Let's take B hats like this, and let's take B hats like that. What direction is the magnetic field force now? So what we want to do, again, fingers in the direction of the velocity vector, and then palm is oriented in the direction of B that's perpendicular to V. So what portion of B is perpendicular to V? None here. There is no perpendicular component of B with respect to V, so the cross product, 0. Theta is equal to 180 degrees here. Theta is equal to 180 degrees. F sub B hat is equal to 0, because the sine of 180 is 0. So those are little tricky ones. We can keep on looking at a couple more here to get it down and make sure that we've got it. So let us say that let's do this. So we've got some charge that's moving, which way is this? Out of the board. So the charge is moving this way, and we see that there is an upward force on that charge. And we say, well, what do we want to know? We want to know the distance here. We want to know what is the direction of the magnetic field then. So what do we get here? Well, we have to have that V crossed into B gives us F. So really, we want to know if V's out of the board, what direction does B have to be so that my thumb is pointing upward, like this. The direction of the force is up, the direction that the charge is moving is out, which means that the direction of the magnetic field must be that way then. And that's what we have then. So we can do all sorts of things like this and say, well, what happens if we've got ourselves like a B hat and we've got ourselves an F's a B hat, switching colors around. What are we looking for? Well, now the missing component here, the missing portion is the velocity vector. What direction is it? Well, we have to have that B, we'll assume that this is the perpendicular component of B with respect to V, that B is, what direction? Into the board. So our palm has to face into the board. And then what do we have? Well, if we want our thumb facing in the direction of F, which means that our velocity vector then must be that way, such that it's perpendicular to F and perpendicular to V. Perpendicular to the perpendicular component of B. So do these over and over and over, but that's what we want to be able to get out of all of this is we've got ourselves a V hat, we've got ourselves an F hat. What are we looking for? Direction of the magnetic field. Fingers going down, thumb has to go that way, which means that our palm is facing out of the board. And sometimes you may find yourself kind of twisted up and trying to make your hand do something that it doesn't want to do. And I say this, my hand doesn't really want to do this all the way like that. That kind of hurts my elbow. Step to the other side. Do something, move. You don't have to be glued to some place and hurt yourself. Step aside. I go like this, it's a lot easier for me to do. Maybe you don't see it as good, but I'm the one that needs to see it, at least for me. Anyways, out of the board. Got ourselves the hat like that. So, given two of the directions, the third one can be found. One you got to be a little bit aware of is that if you are given B, the assumption is that that's the perpendicular component of B with respect to V, unless otherwise stated. But that's just kind of how that is. But there we go. Got all these cross product stuff. Magnitude direction, good stuff. So we'll come back and we'll look at some other things that we can do with these magnetic field forces. Just kind of get this all nailed out there right now. Nailed out? I don't know. Anyways, take care. See you sometime, or you'll see me. Be well.